This is the first chapter of surface chemistry, which is a new chapter. And first of all, we have to know what is surface chemistry, why there is a different separate branch for surface chemistry. So as the name suggests, surface chemistry, so obviously it will deal with all the types of phenomena that are related to surface. Okay, now at the boundary, which is separating two bulk phases. So suppose we have two bulk phases which are touching each other. Now I am not saying that both must be solid, it may be liquid or gas also, but at the boundary that is separating the two bulk phases. So this is one bulk, this is another bulk, but this is the area where these two are touching each other. Okay, so at this boundary, the phenomena that will occur, that is actually surface chemistry. Fine. So if we consider in a wider perspective, it deals with the interaction of surface of one system with that of the other system. Now these two systems, as I have drawn here, it may be solid liquid. So one is solid, another one is liquid. It may be solid gas, one is solid, another one is gas. Then solid vacuum, or it may be liquid and gas. So these are the different possibilities. Now some important examples for these surface phenomena that all of us is very familiar with is heterogeneous catalysis, electrode processes, dissolution, crystallization, corrosion. Okay, so corrosion is it is a natural phenomena, we all have seen it. It occurs on the surface of the metal, okay, that is iron, because mostly when we say corrosion, it is mostly for iron. So the reaction that is taking place between iron and oxygen and moisture, these are the basically starting material for corrosion reaction. Okay, so this reaction, it actually happens in the surface region, not in the bulk phase. Okay, another example is heterogeneous catalysis, and this heterogeneous catalysis, this will be discussed in detail under this chapter. And electrode processes that we have seen in electrochemistry chapter. So here the electrode, and that is if we consider the surface of the electrode, and there are metal ions or anions for non-metals in the solution phase. So this is solid and liquid. So this is the boundary. So at this boundary there will be electron exchange process going on. So that is why electrode, that is electrochemistry, this process is also we can consider under surface chemistry. And then we have dissolution. So very good example is when we suppose you are dissolving salt in water. So if the salt, it is in chunk form, and if it is in powder form, obviously when it is in powder form you can soluble the salt easily compared to the chunk form. Now why it is so? Because when it is in chunk form, then surface area is less, but when it is in powder form, now surface area is high, because there are so many small particles, and obviously surface area will be increased. As surface area will be increased, then dissolution process, that will be faster. And crystallization, suppose we have if we want to purify any impure solid, so we have to dissolve it in a solvent, and if when gradually the solvent will be evaporated, that is concentration will increase. So gradually there will be that is crystallization, that will be started. So first there will be a small particle, then some more solid particles, it will attach to the surface of this, the first generated particle, and gradually the size of the crystal, it will increase. So all these are examples of noticeable phenomena under surface chemistry. Now the subject of surface chemistry, it has many important applications in industry, analytical work, and also daily life situations. Fine. So this is the introductory idea of surface chemistry. Now the first important term that we have to know is adsorption, and be very careful with the spelling. It is AD, not AB, because absorption is something else. This is adsorption. So the accumulation of molecular species at the surface rather than in the bulk of a solid or liquid, that is called as adsorption. Now absorption of, if it is gaseous at the metal surface, then there is a specific name for it which is known as occlusion. So the molecular species that gets adsorbed on the surface, that is known as adsorbate. So these are the molecular species that are absorbed on the surface, so that is why these are adsorbate. And the surface on which the process is occurring, that surface, that will be adsorbate. Okay, actually it will be D. Now solids, particularly in finely divided state, that means very small particles, obviously now the surface area will increase. So that is the reason that charcoal, which is mainly remain in powder form, then silica gel, alumina gel, clay, colloids, metals in finely divided state, all these are very good examples of absorbates because their surface area is very high. Now this colloid, this may be a new term to you, so this will also be discussed in detail in this chapter. Okay, so here you can see, let me erase this. So this absorbent, that is on the surface of which adsorbate molecules will be deposited, that may be solid as well as it may be liquid also. So solid adsorbent, obviously it is more common, right? So that is why you can see here surface area, suppose there is some holes or cracks like this. So if there is some cracks, obviously now the surface area is increased, and in here also these adsorbate particles, molecular species, can be accommodated. Okay, so higher is the surface area, and if there is any cracks or holes, then obviously surface area will increase. And in case of liquid adsorbate, it is D, not P. Here adsorbate, when they are at the surface, that is actually adsorption, but when they are inside the bulk, that is not adsorption. Okay, that is different phenomenon. So adsorbent, it may be liquid or it may be solid, both are possible. Now if we consider del G value in this process, we know the relationship del G is equal to del H minus T del S. So in adsorption, del S basically negative, because just compare, when adsorbate, this molecular species, they are free, that is they are not accumulated on the surface, obviously their entropy is high. But now when they are coming close to each other and they are accumulated on the surface, obviously entropy will be decreased. So that is why this process of adsorption, it involves negative entropy. Now if the entropy is negative, that means there is a negative sign. So negative, it will be positive. So if we want del H to be negative, because for a process to be spontaneous, del G must be negative, but from this we are getting positive, so del H must be negative. And adsorption process, it is basically exothermic. Most of the adsorption process, it is exothermic, so always there is release of heat. So ultimately there is decrease in del G value. So it is accompanied with decrease in enthalpy, that means del H is negative, and also decrease in entropy. So del S is negative, that means now this term will be positive. So del H must be negative, otherwise del G will not be negative. So as a result, finally what we are getting, del G is decreasing. Okay, so this process will be spontaneous. Now the process of removal of adsorbent, and how we can do so, by heating or reducing the pressure of the system. Then this adsorbent, that is removal of, it is absorbate. Removal of absorbate particles from the surface of adsorbent, that process is known as desorption. So adsorption, and the reverse process is desorption. So here you can see, first the molecular species, they are adsorbed on the surface, and when we are heating it, that means we are providing energy, or we are reducing pressure, because when you are increasing pressure, this adsorption process it will be facilitated, but when it is decreased, then desorption, that is now it will be removed. So this is the reverse process of adsorption. Cause of absorption. Now why this process is actually occurring, that we have to know. So in this picture you can see this is the surface area and this is the bulk, right? This is surface. So the molecule B, molecular species, or it may be atom also, it is present at the surface area, right? But A, it is in the bulk area. So the surface particles like B of the absorbent, they are not in the same environment as the particles which is inside the bulk, for example A. So inside the bulk, you can see that they are equally attracted by all the particles surrounding it. But in case of B, that is not the case. Here interaction will be only in one side, but this side there is no interaction. So in case of A, as all the particles surrounding A, there is some interaction going on. So the forces acting between the particles, that will be mutually balanced, because it is surrounding the total three-dimensional area, there is some particles. But that is not the case with B. So obviously here we will have some difference, some unbalanced force will be present in case of B. So surface particles, they are subject to unbalanced attraction by the bulk particles. To satisfy these unbalanced residual forces, now the surface molecules tend to attract and retain molecules of other substances. These other substances are basically adsorbate. These other substances, this is adsorbate particles on the surface with which they come in contact with. So as there is unbalanced residual forces for the particles like B, so all these are basically surface, are in the region of surface. So there will be some unbalanced residual force, and that is the reason they will attract the particles with which they will come in contact. So that is the reason that all these surface phenomena it is occurring, and here we are discussing adsorption. So this is the reason. Now the adsorption process, it will increase when there is increase in surface area, because it is surface phenomena. So obviously if surface area is increased, adsorption will also increase. Now see, with increase in surface area per unit mass of the adsorbent at a given temperature and pressure. So when temperature, pressure, these are fixed, because with temperature and pressure also adsorbent, that is the extent of absorption, it has some relation. So that is why these two variables you have to make it constant. Under that condition, we have to see that when we are increasing surface area per unit mass, what is the effect? And it is observed that when T and P constant, temperature, pressure constant, then with increase in surface area per unit mass of the adsorbent, extent of absorption process is increased. Fine. Now we will see some examples of adsorption, and you will find that some of the examples actually we can observe in our daily life. So control of humidity, this is very common example. You will always find that whenever we buy any new items, there is always a silica gel packet like this found in these items. So these are like this type of transparent beads. So this is silica gel. Now silica gel, it has the property to absorb moisture. Fine. So its main purpose is to help keep the moisture out by allowing the moisture vapor to get absorbed over the surface of it. It may be aluminium gel also or silica. Okay. So the items that we are buying, if we want to keep it free from moisture, then we have to keep this type of silica gel or aluminium gel packet, so that by adsorption process, even if there is traces of water, that is moisture, it will be absorbed and the items will be in dry condition. Okay, so when if you are getting this, do not throw it away. You can use it as desiccant. Fine. Curing diseases. Now we will see how it is related to some drugs. So it is not very surprising that adsorption is also used for curing many diseases. Now, disease causing germs, if they are deposited on the surface of the drug that we have taken, then obviously if this germ containing drug is removed from our body by natural process, then we can be free from this disease causing germs. So in case of drugs, some types of drugs also, we can see the adsorption phenomenon. So curing diseases, that is another example of adsorption. Now pollution masks, it is very common. It allows clean air to reach our nostrils only, because the smoke or dust particles that will be adsorbed on the surface. So there is some filter type of sheet, and this sheet is basically activated carbon element which has property to act as adsorbate. That means on the surface of this activated carbon, these smoke or dust particles which are actually adsorbate, that will be accumulated, and these are actually absorbate. So ultimately we will get only pure air, not full of dust and smoke particles. Next example, purification of water with the help of alum. So during this process, what we do, small piece of alum is inserted in the water. Now in the water there is impurities. So when we are adding alum, it will form some, it is actually coagulant, because it will help to, that is the impurities, to coagulate. So that is why after adding this, there is some formation of coagulant precipitate, and this is trapping the impurities, and ultimately there will be precipitation along with the impurities. So if we can filter it, we can get pure water, right? So during this process, small piece of alum is inserted in water and is allowed to rest. We have to give it some time, and after some time we can observe that the impurities, they are combining and it is forming a large cluster. So this is a cluster, so one can easily remove it by different separation methods. So another example, and you can also say this is the application of surface chemistry. Another important application, or you can say example, is decolorization of matter. So sometimes what happens, because of some undesired substances, if it is present, then there is some formation of color. So actually, suppose if any liquid, when it is pure, it must be transparent, but it is not transparent, it is having some color. That means there is some colored material which is actually impurity. So what we do in this case, we add some decolorizing substances. So these decolorizing substances, basically it will act as adsorbate. Some examples are Fuller's earth. Fuller's earth is basically clay type of material. Okay, this is aluminosilicate type of material, and charcoal. Charcoal is nothing but carbon. So if this adsorbent is added to it, suppose this is the colored water that is full of impurity. So when we are adding to it some adsorbent like charcoal or Fuller's earth, and we are shaking it, then gradually it will be converted to this, and the impurities that will be deposited in the that is in the surface of this adsorbent, and ultimately it will be decolored. Okay, so here we obviously have to filter it. That is not shown here. The final clear liquid you can see here, it is actually water, not necessarily water, it may be any other liquid also. Mostly it is the water. So with impurity it has color, but if we add this adsorbent like charcoal, then these impurities, it will be stuck to the surface of charcoal. As a result, we can get pure water. A very important example of adsorption is heterogeneous catalysis. Adsorbent of reactant, that is absorbed particles, if these are reactants, then what will happen? Now there will be some chemical reaction on the surface. So now this surface, it is actually acting as catalyst. So this adsorbate, which is nothing but this catalyst surface, it is now helping the reactants to convert it to product. So the reactants, it is coming here. So first it is adsorb. So reactants are here adsorbate, and this is adsorbate. So it is forming some intermediate and finally it is converted to product. Okay, that is desorption process is going on here. This is adsorption process, this is finally desorption. So products are becoming free again. So this is the example of heterogeneous catalysis. Now why it is called heterogeneous, why not homogeneous, that will be discussed separately, not now. Fine. There are many gaseous reactions of industrial importance involving solid catalyst. That is, solid catalyst is the adsorbent, and the gaseous reactions, that means the starting materials are gaseous in nature. These will act as adsorbate. So some examples are manufacture of ammonia using iron as a catalyst. So the surface of iron, that will be used as catalyst, and finely divided nickel, because the more it is finely divided, the more will be the surface area, and it is used for the hydrogenation of oils. That is, if there is some unsaturation, hydrogen atoms will be added to it, so unsaturation will be removed. So these two are the examples of heterogeneous catalysis having industrial importance. Another example, production of high vacuum. Sometimes it is required in some experiment, that is high vacuum should be present. So there should not be any traces of air or any other gases. So suppose we have already done the vacuum, created vacuum by some other process, but if there is traces of air, that is if we want it very high vacuum, okay, so what we can do to remove the minimum traces of water, we can add charcoal. So it will be adsorbed on the surface of charcoal from a vessel evacuated by vacuum pump. That is, first you have created the vacuum using vacuum pump, but if still there is some traces of air, this rest of the amounts of air, that can be removed by adsorption process if we add charcoal. So finally you will get high vacuum, which is not possible if you use only vacuum pump. Okay, so this is the utility. Chromatographic analysis. This is also example of adsorption. It is based on the phenomena of adsorption, and this has a number of applications in analytical and industrial field. So here we have a column, and this blue material, it is actually the stationary phase, and this is the loaded sample. There is a green region. Now loaded sample, what is our purpose? Our purpose is, here there is some mixture. Suppose it is mixture of A and B, and you want to make this pure. So you want separate A, pure A and pure B, but there is mixture. Okay, so through this stationary phase, what we will do, first we will load this sample, and after loading this sample, which is containing both the compounds, it may be more than 2 also, A plus B plus C. For simplicity, I have mentioned only 2. So after loading the sample, next step is, now we are adding some solvent. So it is the mobile phase which can move. So that is why it is mobile phase. So this solvent and these two compounds, the solubility of A and B in this solvent that we are using as mobile phase, it is not same. So as a result, what will happen? One substance, suppose B is more soluble, so B will be separated gradually from A. So first A and B, these two are adsorbed in the stationary phase, and the stationary phase is mostly that we take is silica, SiO2, silicon dioxide. Fine. So it is already absorbed. Now when we are adding some mobile phase, that is we are adding some solution, because of the solubility of these two compounds in the solvent, now gradually this band will be moved. So this is the band of, suppose B, this is the band of A. So B is before A, that is it is close towards, first we will get B, then A. So as it will move down, the gap between A and B will increase. So this is the sample separation. You can easily observe the two bands, and B is moving fast, that means it has weaker interaction with the stationary phase and it is more soluble in the mobile phase. So that is why as the mobile phase is going through this column, it is taking with it the compound B, because B is more soluble and its interaction with stationary phase is weak. So that is why it is weaker interaction mentioned here. Now in the next step, see, gradually the gap between A and B is increasing, okay, as it is moving down. So it is having stronger interaction because it is in not close to the mouth of this column, okay. Ultimately this blue band, it will reach here, that is B. So first we will get B and after that we will get A, okay. So this is also example of adsorption, and column chromatography, it is very useful for purification of mixtures. Now adsorption, and there is another term which is absorption. So this is D and this is B. So there is a huge difference between these two processes. The main difference is adsorption, we know already, it is surface phenomena, but absorption is bulk phenomena. That is the main difference. So see, first consider this second point, which is nature. It is a surface phenomena, but it is a bulk phenomena. Now if we want to say definition, it will be accumulation of molecular species at the surface of the liquid or solid or liquid adsorbent. But when it is absorption, it is actually assimilation of molecular species throughout the bulk of the solid or liquid. So it is assimilation, it is not accumulation. Accumulation is surface phenomenon, but assimilation, it is throughout the bulk. Adsorption is always exothermic, that is heat will be released, but absorption is endothermic, heat will be absorbed. Temperature effect, it is favored by low temperature because it is exothermic process, but absorption, it is not affected by temperature. Rate of reaction, it steadily increases and ultimately reaches equilibrium, and it occurs at a uniform rate throughout the whole process. Concentration on the surface of the absorbent, it will be obviously high compared to bulk because it is surface phenomena, but in case of absorption, it is same throughout the material because it is assimilation process. Now there is another term which is sorption, when both the processes take place simultaneously. Now that is also possible. So sorption is basically, it is a combination of these two processes, absorption and adsorption. So there is also some examples of sorption process which is actually involving both the processes together. Now adsorption, there is two broad classification. One is physical adsorption or physisorption, another one is chemical absorption or chemisorption. So when we are saying that it is physisorption, obviously now the adsorbate molecule, sorry, it is D, adsorbate molecules, they are held on the surface of the adsorbent, and here the interaction that is responsible is weak van der Waals forces or any other weak physical forces. So no chemical reaction is involved, no bond formation is there. So this is a picture for physical absorption, it is on the surface. Chemisorption, that is also on the surface, but now see, there is bond formation. So adsorbate molecules are held on the surface of adsorbent on account of chemical forces. So it is chemical force, it is not physical force. And there will be formation of chemical bond. Now the bond may be covalent or ionic. Both are possible. Chemisorption involves high energy of activation because it is chemical reaction actually, bond formation. So obviously there will be high activation energy. So another name of it is activated adsorption. Now sometimes these two processes can occur simultaneously. So it will not be easy for us to determine which type of adsorption process is actually going on. Okay. Physical adsorption at low temperature, it may be converted to chemical absorption when the temperature is increased, because here high activation energy is involved in case of chemisorption. So obviously if we increase the temperature, there will be that is increase in the rate. That means now physical absorption, it will be converted to chemical absorption. So here we have one example. Suppose there is hydrogen and there is nickel surface. So nickel surface is adsorbent, hydrogen is absorbed. So first there is weak van der Waals interaction between the surface nickel atoms and hydrogen atom. And ultimately what will happen? When there is physical absorption, H2 is actually, it is remaining as molecule. So suppose if this is the surface, HH, this is hydrogen, so there will be weak van der Waals interaction. But now if it is temperature is increased, what will happen? Now as we have provided energy by increasing temperature, this bond will be broken. So now we have two individual hydrogen atom. So these two hydrogen atom, that will make chemical bond with the surface nickel atoms. So now it is chemisorption. So in this way, by increasing temperature, these two processes can be, that is physical absorption, it can be converted to chemical absorption. Now we will compare these two. So first of all, see, both these processes are actually exothermic. That is, in general, adsorption process is exothermic. But still you will see that in case of physical adsorption, in effect of temperature is, it decreases with increase in temperature, and that is expected because it is exothermic process, and we know that for exothermic process, increase in temperature, it will be opposite effect on the reaction rate. So it is fine. But see, in case of chemisorption, the effect of temperature is, it decreases with increase in temperature. Increases. First it is increasing with increase in temperature. Now this is not expected for exothermic reaction, but still we are seeing that. Now why it is so? It is because as it involves high activation energy, so obviously to initiate the reaction we have to provide some energy. So that is why when the process is just starting, we have to apply increased temperature, and once it is already started, that is activation energy now already supplied. If we further increase the temperature, now the process, this process will be, rate will be decreased. Okay, so it increases with increase in temperature. That does not mean it is endothermic process. Here temperature is required because we have to provide activation energy. Okay, so just for example, if you see, if you take the example of combustion is always exothermic, right? But still, to start the combustion you have to provide heat. Then it is actually the same thing. Though it is exothermic, still you have to provide heat, otherwise reaction is not possible. In a similar way, in chemisorption also, though it is exothermic, but to initiate the reaction, as it involves high activation energy, we have to provide some temperature, but further increase in temperature, it will decrease the rate of the reaction. Okay, so forces responsible, this we have already seen. Specificity, it is specific but it is non-specific. Now reversibility, it is reversible, but chemisorption, it is irreversible. Okay, next is enthalpy. So enthalpy, it is having very low value, 20 to 40 kilojoule per mole. So this is actually the released energy, because both are exothermic process, so some energy will be released. So the released energy with a negative, here negative sign is not given, but this is the released energy. In case of physisorption, amount is very low, but in case of chemisorption, the amount is very high. Sorry, it is non-specific. I have done the mistake. This is specific. Nature of layer. So it is monolayer mostly, but if you increase the pressure, then some multi-layer formation of adsorbate particles, that is also possible. But chemisorption, it is monolayer. Effect of temperature, we have already discussed it. Nature of gas. It depends on the nature of gas, that is the adsorbate molecular species. This gas, if it is gas, more easily liquefiable gases are adsorbed readily. So there are different types of gases. Some are easily liquefiable, some are not easily liquefiable. So the gases which are easily liquefiable, they are absorbed readily. So if you know the nature of the gas, you can predict which gas will be absorbed more. Here also, in case of chemisorption, depends on the nature of gas, but not in that way that we have seen in case of physisorption. So here the nature of the gas, it is related to whether it will react with the absorbent particles or not. So gases which can react with the adsorbent, only these gases will show chemisorption. The gases which is not reacting, obviously they will not show chemisorption because it is chemical reaction. Okay. Example is accumulation of ammonia on charcoal and chemisorption. This is a very common example that is metal catalyst, hydrogenation using metal catalyst, which is nothing but accumulation of hydrogen on nickel. So here hydrogen will make bond with the surface nickel atoms. Okay. Factors affecting adsorption of gases on solid. So here adsorbate, we have taken gas, surface is solid. Here we have total 4 points, and these points are applicable. Remember, it is for gases on solid. Under that condition, we are discussing these factors: nature of absorbent, adsorbate, gas, pressure and temperature. First of all, we have to know this term, extent of adsorption, which is basically denoted by small x by small m. So here small x is mass of the gas absorbed. Okay, small m is mass of adsorbent. So what is x by m? X by m is the amount of substance, that is the mass of substance, or you can say the mass of the gas absorbed per unit mass of the adsorbent, and that is known as extent of adsorption. So first point, nature of adsorbent, that is the surface on which the process is going on. When we increase the surface area of the absorbent, obviously there is increase in the adsorption process because it is surface phenomena, because absorbing sites will increase now. So that is the reason, if it is finely divided or rough in nature, the surface of the adsorbent that will be increased, and greater will be the absorption process. So when we take metal catalyst, for example hydrogen or nickel, if this metal catalyst it remain in finely divided form, rough nature and porous surface, then they will act as good adsorbent. Okay. A gas can be absorbed on different adsorbent surfaces. This is a very common mistake most of us do, that is D or B, it is always confused. Okay, so be very careful about the spelling. A gas can be adsorbed on different adsorbent surfaces in different amounts. So it depends on the nature of surface. So suppose your adsorbate is common, it is hydrogen, but you have taken two different types of absorbent. One is alumina surface, another one is nickel surface, and it is observed that hydrogen is weakly adsorbed on the surface of alumina, but it is strongly adsorbed on the surface of nickel under certain conditions, that is when other conditions are fixed. Obviously temperature, pressure, these two variables you have to keep it fixed, because we are comparing that changing the nature of absorbent, what is the effect on absorption process. So depending on what type of surface you have taken, the same adsorbate, the adsorbent process that will be different. Okay, it will be better in case of nickel surface. That means nature of adsorbent, it has some role. It affects the process of adsorption. Next is nature of adsorbate, and here we have taken gas molecules that adsorbate. Same adsorbent. Now we have same adsorbent, that is surface area is common, temperature fixed. It can absorb different gases to different extent. So now surface area is constant, but we have taken different gases. So adsorption process, absorption process that will be different, and it is related to, that is the extent to which gases will be adsorbed, that is proportional to critical temperature of the gas. Now what is critical temperature? That we have to know. So critical temperature is that temperature, it is mostly used for gases, above which the gas cannot be liquefied. Okay, so suppose if I am saying that critical temperature of a gas is 50 degrees centigrade, it means when the gas is under temperature greater than 50, that is suppose if the temperature is 60 or 70, then obviously we cannot liquefy it. But if it is under 50, that is 40 or 30 degrees centigrade, then you can liquefy it. So 50 degrees centigrade, it is the critical temperature of the gas, above which we cannot liquefy the gas. Greater the critical temperature of a gas, greater will be its liquefiability. Okay, because the range now it is increased. Suppose one gas having 50 critical temperature, another gas is having 80 critical temperature. So obviously now you are getting a larger region, that is range is increased. So that is why higher is the CT critical temperature, higher will be the liquefiability, and greater will be the adsorption process, and vice versa. That is, if CT is very low, liquefiability process, that is liquefiability, it will be very low, adsorption will also be low. So the reason is that easily liquefiable gases, their intermolecular forces of attraction is very high. So that is why they are easily liquefiable, because liquefiable means what? It is gas molecules, they are in gaseous state, and when you are making it liquid, obviously now the particles are coming close together, and when it will be convenient when the intermolecular forces of attraction is very high, that means they can easily come close to each other. So it is easily liquefiable. So easily liquefiable means higher intermolecular forces of attraction, and as a result they will be strongly adsorbed. However, in chemical absorption, so this is about physical absorption that until now we have discussed, that is related to CT and liquefiability. This is all for physisorption. But if it is chemisorption, there is no such relationship, because it occurs only if the gas can form a chemical bond. So this point we have already seen when we have compared physisorption and chemisorption. There you have already seen that this type of critical temperature relationship, that is only for physisorption, not for chemisorption. So here we have definition. CT is that temperature above which gases cannot be liquefied no matter what the pressure is. That means even if you increase the pressure, once it is greater than it has already crossed CT, you cannot make it liquid. Above critical temperature, increase in pressure won't let liquefaction of gases happen, because now the gas molecules above CT, they have sufficient kinetic energy so that they can overcome the intermolecular forces. So now the effect of kinetic energy, that is winning over the effect of intermolecular forces. So as the kinetic energy is very high, molecules, they will not come close to each other, and if they are not coming close to each other, how we will make it liquid? Fine. So this CT related problem you can get, it is very common. So what the type of question that you will get is some critical temperature. Sometimes it will be given and sometimes it may not be given. So some examples of gases, 3 to 4 gases will be there, and you have to predict that among these 4 gases which one will be adsorbed very easily. So if critical temperature is directly given, it is very easy to predict, but if it is not given, it is better you try to remember the values of critical temperature of some of the common gases. Here we have a table with critical temperature. So this is the gases, this is CT value in Kelvin. Fine. So here you can see water, then ammonia, HCl, all these are having very high CT. So greater the CT, greater is the liquefiability. Actually water, when we have considered, it is already in liquid form, but it also has gaseous form, which is vapor. So with respect to vapor, you can consider as if it is gas, and when you are make it liquid, it will be converted to liquid water. So from this critical temperature, now you will be able to understand which gas will be adsorbed compared to some that is absorbed in higher amount compared to some other gases. Fine. So this is the nature of adsorbate molecules. Third point is pressure. Adsorption increases with increase in pressure, directly proportional of the adsorbed gas, and this increase is most significant when temperature is low. But if temperature is very high, as it is also dependent on temperature, so there will be some other process going on. So that is why when the temperature is low, then only we can say that it is directly increasing with increase in pressure. Extent of absorption directly proportional to small pressure ranges only because it achieves a limiting value at high pressure. So what it means? Suppose you are increasing pressure. Now one value when it is reached, one value of pressure, particular value when it is reached, suppose the adsorption process is called complete, that is all the surface area all are covered. So after it is completely covered by adsorbate particles, after that even if you increase the pressure, there should not be any further adsorption process because that is not possible. On the surface area it is covered. So that is why there is a limiting value. It is called saturation pressure. After this saturation pressure, with increase in pressure, there will be no effect. Okay. So all the surface adsorption sites are saturated because there is a fixed number of adsorption sites. Okay. Where gas molecules can be absorbed. Temperature. Physisorption is exothermic process. Actually, chemisorption is also exothermic process, but as we have to explain it, how we can explain it, as it is exothermic process. So according to Lee-Chatelier principle, when we are increasing temperature, there will be decrease in the extent of adsorption because in this process energy is released. So according to Lee-Chatelier principle, if a system it is already in equilibrium and if you are making some disturbance to the equilibrium by changing temperature, pressure, concentration, etc., then the system will try to minimize all those effects. Okay, so that is why when we are increasing the temperature, so this is a disturbance we are giving to the equilibrium. So now the system, it will try to minimize this excess energy. So what it will do, now the backward process, that is desorption, that will be more. That means decrease in the process of adsorption. So that this excess energy it can minimize, because in the process already energy is generated and further we are adding more energy. So obviously the process will be slow. But when it is chemisorption, remember this is also exothermic, but as it involves activation energy, so to initiate the reaction we have to provide some amount of energy in the form of temperature. So adsorption increases initially, but suppose already it has obtained the required activation energy and now you are further increasing the temperature, now there will be decrease because ultimately it is exothermic. So that is why it will, after a particular temperature, it will decrease as temperature increases further. So if you look at this graph, it will be very clear the nature of extent of absorption, which is small x by m, how it is dependent on temperature T. So if it is physical absorption, then under constant pressure, because it is also dependent on pressure. So if you want to know what is the effect of temperature, obviously pressure should be constant. Okay, so that is why in both cases pressure is constant, and under that condition the extent of absorption, that is small x by m, see, with temperature it is gradually decreasing. So suppose this is temperature 1, this is temperature 2. So at temperature 1, if you draw a line, this is the value of x by m. But at temperature 2, if you draw a line, this is the value of x by m. So it is very small compared to this point. So it means with increasing temperature, x by m, that will decrease. Now come to chemisorption. See, here with increase in temperature, one point will reach when it is maximum value. But on both sides of this temperature, that is in the left hand side and in the right hand side of this temperature, in both cases it is decreasing. Okay, so this is the nature of that is change in extent of absorption with increase in temperature in case of chemical adsorption. Adsorption, isotherm. So isotherm means it is constant temperature process. So that is why it is isotherm. We know that there are different terms for different constant variables. That is, if it is constant pressure, we called isobar, isochoric process, isobaric process. So it is isothermal. That is, from isothermal process the term is coming isotherm. So variation in the extent of absorption, which is small x by m, with pressure at constant temperature. So now we are trying to see what is the effect of pressure on x by m. So we have to keep the temperature fixed because both are variable. One variable must be constant. It can be expressed by means of a curve termed as adsorption isotherm because constant temperature. So different adsorption isotherm was studied by different scientists, and according to the name of the scientist, there is a specific name for all these isotherm. Freundlich adsorption isotherm, according to the name of the scientist Freundlich. So he proposed an empirical relationship between the amount of gas absorbed by unit mass of absorbent, which we call extent of adsorption, small x by m, and pressure at a particular temperature, and he found this is the relationship. So x by m, it is proportional to p, and p is having this power 1 by n. Here k is constant, n is also constant, and n is having value 0.1 to 0.5. This is the range, and which depends on the nature of the adsorbent. That is, these two constant, though we are saying these two are constant, but they are dependent on the nature of the absorbent. That means if you want to know what is the effect of pressure, absorbent must be fixed, because this is another variable on which absorption is dependent. So under the condition temperature is fixed, adsorbent is not changing, it is fixed, then only we can compare how x by m is changing with pressure. So it depends on the nature of adsorbent and the nature of gas also at a particular temperature. That means at a particular temperature means what? It is also temperature dependent. That is why it is mentioned at a particular temperature. So though we are saying k and n constant, but remember these are dependent on these variables. Here we have this curve x by m in y-axis, pressure in x-axis. So different temperature you can see in Kelvin scale. So when there is increase in temperature, gradually x by m, that is decreasing. That means extent of absorption is decreasing with increase in temperature. So this observation, in which case you have observed? You have observed it for physisorption. But if it is chemisorption, the nature will be like this. There will be a hump. But particular this picture, this is applicable for physisorption. Okay. Now see, here we have stopped the curve here. But maybe if it is further extended, maybe the nature is like this. That is, again it will decrease. Fine. but if the curve is like this, that means it is for physisorption. And in this curve there is only one line. This is also x by m versus p. And see, at this particular pressure, which is saturation pressure Ps, after this pressure what happens? The line becomes parallel to x-axis. Now parallel to x-axis means what? Now the value of x by m, it is fixed at this point. That means now all the surface sites, that is adsorption sites, are occupied. So after that, even if you increase the pressure, there is no effect, obviously, because saturation point is reached. So that is why this pressure is known as saturation pressure. Extent of adsorption at different pressure. Now see, in the previous curve you have already seen that the value of n, it has a particular 0.1 to 0.5. okay, so this is having a range. But suppose if this range, it is not in this range, then what will happen? So in this graph we have basically total 3 regions. This is one region. So in this region it is almost like straight line which is going through origin. So this type of straight line, when we observe it for this type of equation, like y equal to mx. Okay, so there is no power of x, that is the power is basically 1. So here the power of p is 1. That means 1 by n is 1, and 1 by n 1 means n is also 1. So at low pressure, so this region is actually low pressure. 1 by n is 1, that means n is also 1. X by m, that will be directly equal to k into p, because now the power of p is 1. So basically, as k is constant, x by m, that is the extent of absorption, now it is directly proportional to p. So as you are increasing pressure, this is also increasing. So it is directly proportional to pressure. So this is the first observation. Now if you consider this region, okay, that is A to B, now what will happen? Now it will follow, that is x by m, it will follow the equation that you have seen in actual Fronley's absorption isotherm. Okay, so that means Fronley's absorption isotherm, it is applicable because here n has some particular value. It is applicable only between these two range. But if pressure is very low and if pressure is very high, this is high pressure, this is low pressure region. So after this point, when the pressure is very high, that is after PS, that is PS, saturation pressure, then what will happen? Now at high pressure, 1 by n is basically 0. Now something to the power 0, that means what? It is actually equal to k. So now x by m, this is fixed. It is not dependent on pressure. It is independent of pressure, and x by m, that will be equal to k only. So it is a constant. So that is why now x by m, there is no change. It is actually a straight line, almost straight line. Okay, so these three in this curve, basically 3 regions are there: low temperature, low pressure, intermediate pressure, and high pressure. And remember, this Fronley's absorption as well, it is applicable only in this temperature region, pressure region. Okay, intermediate pressure. So for different adsorbent and adsorbate combination, this saturation pressure, this will also be different, because this is dependent on the nature of adsorbent and adsorbate.